2, for those of you who missed the notes today, we're going to start our talk about logs as inverses, or logarithms as inverses. Okay, so, inverses. We have lots of inverses that we know. Addition and subtraction are inverses. Multiplication and division are inverses. They sort of undo one another. X squared and square root of x are inverses. So these are all inverses. Well, guess what? Exponential function has an inverse, okay? An exponential function has an inverse, and it's a log. So expo and logs. So we'll talk about what logs mean here in this video. And this is just the tip of the iceberg, so we're going to take this much further as we go through the section. Okay, so we're going to start with an exponential to solve an exponential equation. So we've been solving quadratics, polynomials. This is an exponential. So this is just saying 2 to what power is 16? 2 to what power is 16? And you probably can go ahead and say, oh, well, that's 4. 2 times 2 times 2 times 2 is 4. So this answer is going to be 4, and that's correct. But the process that is happening here, behind the scenes, is that both 16 and 2 are a base 2. So 2 is 2 to the first, and 16 is 2 to the fourth. All right, so if you can write them in the same base, and you certainly can, if you have base equal to base, then exponent has to equal exponent. So I can cross out that 2. If you have the same base, the exponents have to be equal. Okay, so you can just cross out the base, and you can just solve up in the exponent position of x equal to 4. All right, so that's great. Doesn't seem like we need logs yet. But what about this one? 2 to the x is 10. Well, I can't write 10 as a base 2. 10 is not 2 to some power. We got 2 to the first, which is 2, 2 squared, which is 4, 2 cubed, which is 8, and 2 to the fourth, which is 16. So I know this is going to be somewhere between 3, because that would be 8, and 4, which would be 16. And what it actually is I'm going to use my calculator this is what you're going to learn to do. It's actually 3.3219. Now, I just did that over on the side here on my calculator. So, how in the world, and, just to see what we're doing there, 2 to the 3.32919, 3219. Yeah. All right. You'll see that that's actually equal to 9.9999, which is basically 10. I rounded here. So this is what we're going to be finding, okay? And you can see that 2 to the 3.3219 equals 10. So how in the world are we going to find this number on our own? How in the world are we going to find this number on our own? We would never just know that by mental math or anything. We need logarithms. Okay? The logarithm, I don't have it spelled right. I've got this middle piece here, logarithms. There we go. Okay, there we go. All right, so every exponential equation can be written in log form. Okay, and so what you're going to do is look at, this is the base. All right, and so a logarithm has a base. Okay, so we've got a log here. So here's exponential. Every log has a base, and the base goes right down here as a subscript. It goes diagonally down below, and that's its base. So base, kind of down here in the basement, if you will. So that's the base, raising to the x. Log has a base down here, so we write it down here. So for here, this 2 is going to go, there's this little subscript right here. Okay? And then you set the logs equal to the exponent. On the other side of the equal mark is always the exponent. So this exponent of 2 will always be on the other side of the equal mark. Okay? So here, this exponent of x will always be on the other side of the equal mark. Log equals the exponent. All right, and so the other part that's left is what the exponential equals, and that goes behind the log. So up here that goes behind, that's called the argument or the component of the logarithm. All right, so this is exponential form, and this is logarithmic. Form. Okay. Okay, so first thing we're gonna do is convert each equation into log form. We're gonna start with the base. I start with the base on both of these. So the base is 10, so I'm gonna write log, put the base in the basement. Okay, we're gonna have an equation on both sides. Remember, log equals the exponent. So the exponent is 3, and then this, what the exponential was equal to is tucked back here. All right, so same thing here, log base 81, and it has to equal that. Let's get that one up. Log base 81 has to equal that exponent, and 3 gets right here. All right, and then the last one, log base, that's 5, has to equal the exponent, and then 1 over 25. Okay, so let's examine these, a little more closely. I mean, certainly 10 cubed is 1,000. This is the fourth root of 81, which is certainly 3. And this is, 1 over 25, and that's 1 over 5 squared. So these are all sound. 1,000 is certainly 10 cubed. The fourth root of 81 is certainly 3, and that's 1 over 5 squared. Okay? So now when we go backwards, we're just going to circle around the problem to transition back. I call this circling around the problem. I still start with the base, and I do what I say, circle around. So if I were to transition and just look at these and kind of go back and forth, I would go 10 cubed is 1,000. 81 to the 1/4 is 3, or the fourth root of 81. 5 to the negative 2 is 125. Okay, so that's how we're going to go in this direction. So start at the base. 2 to the 5th equals 32. And what you write down should make sense. 2 to the 5th, is that equal to 32? You bet. 144 to the 1/2. Okay. 144 to the 1/2, is that equal to 12? You bet, because remember that's the square root of 144. And last one goes this direction, 3 to the negative 3, is that 1 over 27? 3 to the negative 3, and yes, that would just be 1 over 3 cubed, and that certainly equals 1 over 27. Okay. All right, when the base of the log is 10, then it's called common log. All right, so if you look on your calculator, there's only 2 logarithms on here. This log, and if you look up, it says 10 to the x. So this is your common log. It has a base 10. Notice there's no 10, directly below it. There's no 10 in the basement. But above it, you can see that 10 to the x. Above it, you can see that 10 to the x, so that kind of reminds you it's based on. And this is also a logarithm. We'll talk about this later on. This is the natural logarithm, ln, or the logarithm natural, or natural log, and it has a base of e, but that's coming later. So right now I'm focusing here. So when you have, this is going to be written as log 12. Okay? You're not going to see this 10 very often, but you know it's there. So right here, when it's log base 10 of 5, you'll just see log 5. You know that 10 is there, but it's understood. And so your calculator is ready to compute these. So we're going to do log of 12, and you get 1.079. Okay, so what does this even mean? This is 10 to the 1.079. And does that equal 12? Well, we're going to check. But think about it. If it was 10 to the first, it'd be 10. If it's 10 squared, it'd be 100. So it's got to be pretty close to 1. And so let's take that 10 and raise it to 1.079. And sure enough, we get pretty close to 12. All right? And then this one here is just that. We're going to do log of 0.5. And we get negative 0.301. And if you wanted to check that, you know, is 10 to the negative 0.301. Is that pretty close to 0.5? And you can see that it is. So that's what we're finding here. You know, 10 to the negative 0.301 is equal to 1/2. All right. So that still doesn't help me find this one. Okay, this is a base 2, not a base 10. Sure, it equaled 10, but it's not a base 10. So what the calculator has with log base 10 is not helping me with the base 2, so we'll learn how to deal with this later. But this is the big picture of what we're trying to get to in this section. So we can write any power, any number as a power of another. Okay? So to solve a base 10 here, you know, 10 to what power is 31? I have no idea. I mean, I know 10 to the first is 10 and 10 to the second is 100, so I know it's going to be 1 point something, but I don't know that decimal equivalency. So we're going to convert to log form since our calculator is ready and it's base 10. So log base 10 in the basement of 31 has to equal that exponent. Okay, and again, you don't have to write that 10. Log 31, 1.491. Okay, and 10 to the, and I'm even to retrieve the answer, and you'll see you get 31. So I didn't round, I just retrieved that whole answer, and I got 31 exactly. All right, next one. All right, log form. Log base 10 of 3 over 49 equal to x. Go to calculator. And I get negative 1.213. That's a point. And let's raise 10 to that answer. All right, and let's see what 3 over 49 is. All right, so perfect. We got the exact answer there. All right, so let's graph these. Let's do a little bit of a review. Okay, if I graph here, 2 to the negative 2, that's 1/4. Okay, that's just 2 squared, which is 4, but it's in the wrong place, so 1 over 4. 2 to the negative 1, that's 1/2. Anything to the 0 power is 1. 2 to the 1 is 2. And 2 squared is 4. And so goes the exponential graph. Have asymptote here. So graph the inverse. Well, I'm going to switch x and y. All right, so let's take our t-table and switch them. So at 1/4, I'll be at negative 2. 1/2, I'll be at negative 1. 1, 0, 2, 1, 4, 2. Right? Okay, so here's this graph, and this is the normal curve for log. So this is, I'm going to write the equation here in just a minute, but this key value here is 0, 1. Okay, and the key value on the logarithm is the reverse, and that's where this graph really starts to take off, and then that's where this graph really kind of starts to kind of do this shape over here. As for an asymptote, x and y are going to switch, so now it's x equal to 0 for the logarithm. All right, how does this look? So this is your y equals 2 to the x here. How does it look as an equation? Find the equation of the inverse. So we're going to switch. And then I'm just going to write this in log form. So log base to the basement 2. Okay. It's got to be equal to the exponent. And so this x comes here. So sometimes, students think of it kind of switching. All right, so the equation of the inverse is y equals log base 2 of x. So this is y equals log base 2 of x. And there you go. So log base 2 of x. So notice this domain here is everywhere, all reals. Okay, and it is strictly above the x-axis, so y is greater than 0. So these domain and ranges, just like x and y are going to switch, these are going to switch. So the domain, all reals, becomes the range here. So y is an element of the reals. And now you can see that there's y values everywhere. It goes infinitely down and infinitely up. But now x is to the right. Y is above on the blue, and x is to the right on the pink. So this is x greater than 0. Okay, and so this next piece, graph log base 3. All right, so remember this is coming from basically y equals 3 to the x. Okay, y equals 3 to the x. If you switched x and y to do the inverse, then this is how it would shake out. Well, this has that key value, okay? That has the same key value. If we put in 0, we're going to get 1. So my logarithm is going to have that key value of 1, 0. It's also going to have this asymptote. Okay, the domain x will be greater than 0. The range is all reals. Now instead of a y-intercept, we have an x-intercept. And this asymptote of x equal to 0, and it's below. All right, and the graph is going to behave just like this. All right, so that is y equals log base 3 of x. Now, if we were to transform it, this would be a horizontal shift right 2 and a vertical shift up 3. So the new domain and the new range. All right, let's look at the key value here. The key value on the original is 1, 0. So this is going to be plus 2 on x. Horizontal shift right 2 is going to be, it's going to be a plus 2 on x. And a vertical shift of 3 is going to be a plus 3 on y. So the key value will go plus 2 on x, plus 3 on y. It'll now be 3, 3. That shift right is also going to change the asymptote. This is going to be plus 2 also. Since it's an x equal, the new asymptote will be x equal to 2. All right, so let's graph this over here in blue. The new key value is 3, 3. The new asymptote is x equal to 2. And so it's just going to travel up, hit that key value, and then go that way. So the range hasn't changed at all. It's still infinitely up and infinitely down. But the domain has changed. So now instead of being greater than 0, we're going to be greater than 2. So that also gets that shift. That also gets that shift right too. All right, so that is 7.3. Hope that helps for those of you who missed the notes. All right, and we'll see you in class soon. Bye.